All right, let's get started again. So now we're going to be talking about the main tool of hypothesis testing, so-called p-values. And p-values really address the problem that you just saw a moment ago in this epsilon test question. Likelihood does not provide an absolute number whose meaning can just be interpreted in terms of that number. Like a likelihood of 0.5 doesn't mean anything. You know, maybe a likelihood of 10 to the minus 27 would actually be really good for your model, and you should accept the model in that case. There's no absolute meaning to that number. P-values provide you a tool where just the value of the number is directly meaningful as a number. Like p-value less than 0.5, that tells you something. What exactly it tells you, we're going to go into detail. So it is something that can be used for rejecting an individual hypothesis, just on the absolute value of the p-value given that hypothesis. As you'll see in a moment, another name for this is a so-called extreme value test. So here's the idea. We are building on top of this platform of the likelihood, but instead of talking about sort of what you might think of as the probability density at a particular value of x, instead we're talking about the cumulative probability for all values of x that are more extreme than some chosen cutoff. So this is typically written in this kind of form here. Let's say that we're looking for small values of x, and we have some particular observed value, which I'm going to indicate as lowercase x. Let's say that's a value that we actually observed experimentally. And we're asking the question, what is the probability under our hypothesis that the random variable x would have a value less than or equal to our observed value lowercase x, okay? So I think you can see that for a continuous variable x, this would be an integral, right? And if you want this extreme value, p-value, would be simply equal to the integral from negative infinity to little x of the probability of our random variable x given h0. So it's sort of like we've got some probability distribution, and at some particular cutoff representing our observed value little x, and this x-axis is our random variable x, and our y-axis is the probability density for x. Basically, we're going to integrate this slice and would give this extreme value test referred to as a p-value. Okay? Any questions about this definition? Okay, so the one little twist that you need to be mindful of here is there's a question about whether what kind of extreme you're looking for. Are you looking for extremely low values? Are you looking for extremely high values? Are you looking for values that just deviate far from the mean? You would actually devise different p-value tests for those three cases, right? So if we're looking for small values of x, then we would use this form. If we're looking for big values of x, we would use this form. if we're looking for extreme deviation from the mean, mu, then we would use this form, okay? I'll get in a moment into the question of why would you be looking for big, little, or highly deviant values? What drives that choice? Any questions about this? Okay, so hopefully from the epsilon test question, you'll see why we need to do this. We've made what might appear to be a very subtle little change in talking about just a likelihood with an equal sign to a p-value, where now that equal sign changes into a greater than equal sign or a less than or equal sign, depending upon whether you're looking for big deviations or small deviations. So the difference here is that the likelihood, that's just a probability density. The actual density value as a number is not meaningful. By contrast with a p-value, now we're talking about a cumulative probability, so it's no longer arbitrary, just what the local density is. It's talking about the entire probability range, so it's a true probability as opposed to just a probability density. So we would use this then to measure the probability of all values of our random variable above some threshold. Okay. So as I said, the main issue then is to just get the direction right. So any questions about the definition of a p-value or why we're switching over from just using straight likelihood to using a p-value as a hypothesis test? Okay, well, to see how this works in real life, why don't we try doing an exercise to actually use this. So as a preliminary, let's use some nomenclature to kind of nail down exactly what we mean by a so-called p-value test. So the idea here is that from our original random variable x, representing our observable, we can create a new variable, random variable that I'm going to call t. It's our test variable. And because I can write down a mathematical rule that automatically for any observed value of x gives me absolute certainty about what value of t I would get. Therefore, I think you'll agree that t meets our definition of an observable variable, right? There's no uncertainty about the value of t given our observed value of x. So what is the meaning of t? Well, we choose it to be defined relative to a cutoff value alpha for our p-value. So basically what we do is once we define a p-value as an extreme value test, we choose some threshold alpha. Let's say it could be alpha equal 0.05. That's a common confidence cutoff, right? For 95% confidence, you choose a 0.05 cutoff for alpha. And we would say basically we would call this as t plus if the probability of getting this observation or something more extreme than this under our H minus model is less than our alpha cutoff, then we would call that a positive test result. In other words, it is rejecting H minus. Okay? On the other hand, if our p-value is not less than or equal to alpha, then we call this as a test result t minus. In other words, it's consistent or at least not incompatible with H minus. It is not rejecting H minus. Okay? So the one thing that hopefully is clear from the definition of our variable t is that by definition the probability of getting t plus given H minus is just alpha, because that's where we set the cutoff, right? We set that probability to be alpha. Okay, so now we can plug this into our Bayesian framework for asking questions about the probability of H minus. A few more little details to bear in mind. What if we apply this test not to just to a single value of x, but to multiple values of x? So this would be like doing n independent p-value tests on n different values of x drawn from our data set. So remember that the false positive rate expected under this definition, probability of getting t plus given H minus, is just alpha. So if we do this n times, how many false positives do we expect to get under the H minus model? Well, we just expect to get n times alpha false positives, right? So if we want out of this whole data set to get fewer than beta false positives, that tells us what threshold we have to set alpha at in order to design in that number of false positives. So this is commonly referred to as the Bonferroni correction. What it's basically pointing out to you is if you use a p-value not just once, but you apply a p-value test to multiple data points, of course the number of false positives that you're going to get is going to go up and up and up as you apply it more and more times. So you must not make the mistake of thinking that alpha is going to be your number of false positives when you do it on this large data set. No, it's going to be n alpha, and so if we want beta to be small, we have to set alpha to beta over n. Okay? Any questions about?
Yeah, I didn't get the point of why I would expect n alpha for false positive.
So this is our false positive rate. Do you agree about that?
Yeah.
Okay. So this false positive rate by definition is alpha.
Yeah.
If we draw n values of x, how many cases of t plus would we get if we were drawing x straight from H minus? In other words, the truth is H minus, and we're just drawing values of x from H minus, and occasionally we're going to get a t plus from that value of x, right? How often? That often. What's the probability of t plus given H minus? It's just alpha. So if we repeat that procedure n times, how many t pluses will we get on average?
Oh, I see.
N alpha. Other questions? Okay. So